Now we come to Archimedes' principle for a floating object. So it's not fully submerged like it was before. So some of the volume is outside and some of the volume of the solid is inside the fluid. The volume inside the fluid, we're going to call V fluid, okay? And the volume outside is going to be part of the entire object, okay? So when we refer to V object, we're referring to the part volume. So we're now going to consider the case where the object is not fully submerged. So the solid is not fully submerged in the liquid, but can float. It may be partially submerged, okay? So we're just going to look at that. We're going to assume that the object is in static equilibrium. That means it's not moving up or down or sideways. It's in equilibrium. The upward buoyant force, which we know there's always a buoyant force when an object is immersed fully or partially in a fluid. So the upward buoyant force is balanced by the downward force of gravity, hence we have equilibrium. Yeah? The volume of the fluid displaced corresponds to the volume of the object submerged. Yeah? So here's my object, it is partially submerged, and this is the volume of the fluid that is displaced, the volume of the object which is submerged. That's my V fluid. Yeah? So my two densities, the density of the object and density of the fluid, are in a ratio which is equal to the volume of the fluid divided by volume of the object. Yeah? So inversely proportional density and volume relationship. Then we have mg for the object's downward weight being equally balanced by the buoyant force upwards. Okay. Let's do a simple problem. Calculate the buoyant force on a 2-liter helium balloon given that the density of air is 1.29 kgs per meter cubed. So what is my buoyant force on the object? Let's just change the color here. Okay. The buoyant force is going to be equal and opposite to the weight of the fluid displaced. Yeah? The fluid is the air in this case. Fluid, it could be a liquid or a gas. mg. Yeah. I'm going to write of the fluid. So this is going to be rho of the fluid times volume of the fluid times g. Yeah. What is rho of the fluid? That's given here, 1.29. What's the volume of the fluid? It's the entire volume of the balloon. That volume is displaced. We need to convert liters to meter cubed. Okay, so we have 1 liter equals 10 to the minus 3 meters cubed. You're going to need this conversion. Okay, and then you know G. So you should be able to work this out using your calculator. Yeah? Substitute in the values, use your calculator, and you should get the buoyant force as 2.5 times 10 to the minus 2 newtons. Okay? Let's look at another question. In an immersion measurement of a woman's density, she is found to have a mass of 62 kgs in air, that's her true mass, an apparent mass of 0.085 kgs when completely submerged with lungs empty. So this is the case of being completely submerged. Look at how much her mass has dropped. She is virtually massless, yeah? Because of the buoyant force. What is her volume? So you just need to find that buoyant force. It's going to be equal to the true mass, true weight, and subtract out the apparent weight. Yeah. So the true weight is her weight m1g here, M1G is her true weight in air. Weight in air. And MAG is her apparent weight in water, right? I'm going to subtract one from the other to get the weight of the fluid displaced. This must be my buoyant force. I'm going to write that buoyant force. I know its expression, so I'm going to use that weight of the fluid displaced. M times W must equal volume times density, yeah? And we use these expressions in buoyancy when we're calculating that. So substitute in your values. This is the density of water, and that's going to give you 0.062 meter cubed. That's the volume of her lungs, okay? This is maybe a slightly more complicated question. You'll probably get a more simple question than this. Let's look at another question. If your body has a density of 995 kg per meter cubed, what fraction of you will be submerged when floating gently in fresh water? So you're just going to take the ratio of the densities and set them equal to the ratio of the volume. The second question is identical, just for a different system. So we're just going to talk you through the results of the first one. Here's my ratio of the object density to the water density. That's going to tell me the volume submerged. So volume submerged is 995 divided by 1,000. That means 99.5% is submerged. Similarly, you're going to find out in part B how much of the ice is submerged, and you should get 91.7%. Pretty straightforward. Thank you.